Welcome to the Deep Dive. This is where we take a whole stack of information, zero in on what really matters, and try to build some understanding together.
Mm-hmm.
And this time, we're continuing our series looking at the online encyclopedia of integer sequences. Specifically for you number theory students out there, we're tackling sequence A000245.
Right. A fascinating one. We're going to explore its, let's say, mathematical origins, and then see how it connects, maybe in ways you wouldn't expect, to binary trees. Specific concepts there.
Okay. So we've got the OEIS page for A000245 itself, naturally.
Yep. And some foundational stuff on binary search trees, complete binary trees.
Yeah.
One of the textbook materials students often see.
And even a glimpse of some online discussion, like a Reddit thread, maybe showing how these ideas get talked about in practice.
Exactly. So the mission is to, unpack all this and see how an abstract-seeming sequence links up with these, well, very concrete data structures.
Seeing the forest and the trees, you might say.
You might.
So if you're into number theory, use the OEIS, or just, love finding those hidden connections in math, this should be interesting.
Definitely. So let's start with the sequence itself, A000245. The OEIS lists the first few terms as 0, 1, 3, 9, 28, 90, 297, 1001, 3, 4, 32, and so on.
Okay. 0, 1, 3, 9, 28. Not immediately obvious, maybe. What's the definition?
Well, the OEIS page gives a defining formula. It's AN equals 3 times 2, that's factorial, divided by the product of n plus 2. And N1.
Whoa, okay. Lots of factorials. That usually screams combinatorics, doesn't it? Counting things.
It really does. But the OEIS provides a perhaps more familiar connection right off the bat, especially for number theorists.
Oh.
Yeah. A really key point on the page is its relationship to the Catalan numbers, that sequence A000108.
Ah, Catalan. Okay, those I know. Balanced parentheses, paths on a grid. They're everywhere.
Exactly. And this sequence, A000245, specifically AN, is the first difference of the Catalan numbers. So AN, Catalan plus 1 minus Catalan.
Interesting. So it's built directly from them.
Right. And there's another formula mentioned for n greater than 0, but n equals 3n divided by n plus 2 times Catalan. So very tightly linked.
Knowing it's tied to Catalan numbers is a huge clue then, because Catalan numbers count so many different structures.
It absolutely is. And the OEIS page for A000245 backs this up. It lists numerous different combinatorial interpretations, basically different kinds of things that this sequence counts.
Okay.
And this is where we start seeing hints of tree-like structures.
Mm-hmm.
For instance, one interpretation is that AN counts the number of Dick paths of length, 2n plus 1, that start with 2 up steps.
Okay, hold on. Dick paths, those are the grid paths, up and right steps, or up and down, depending on convention, that don't dip below the diagonal, right?
That's the usual idea, yes.
And Catalan numbers count the standard Dick end path. So A000245 is counting a specific type of Dick path, ones that are a bit longer and start a certain way.
Precisely, a specific subset. And the OEIS source gives other interpretations too, like certain lattice paths touching a line, permutations avoiding patterns.
Mm-hmm. Right, the usual combinatorial zoo that OEIS is so good at cataloging.
But critically, for our discussion, it also lists interpretations directly in terms of trees.
Ah, okay.
It says it counts rooted trees with n plus 1 nodes where the root has degree greater than or equal to 2.
Degree greater than or equal to 2. So the root has at least 2 children.
Yes. And another one. Rooted trees with n plus 2 nodes where the root has degree at least 1 and the rightmost path has length at least 2.
Okay, now we're talking trees directly. So it's not just that it's related to things like Dick paths, which can be mapped to trees. The OEIS is saying this sequence literally counts certain kinds of rooted trees.
Exactly. That's a much stronger, more direct link than just the Catalan connection, although that's related, of course.
Yeah.
These specific tree interpretations listed in the OEIS are crucial.
So A000245 doesn't count, say, all binary trees of a certain size or anything that simple.
No, not all of them. It's counting very particular subclasses defined by these kinds of properties, the root's degree or something about the structure of the rightmost pass, things like that.
Got it. Okay, so let's maybe put a pin in A000245 for a second, knowing it counts these specific trees. Let's talk about the tree structures themselves based on our other sources, binary trees.
Right. Good idea. So one fundamental type is the binary search tree, the BST.
The classic.
The classic. And the sources define it as, a rooted binary tree where for any node, the key or value in that node is greater than everything in its left subtree and less than everything in its right subtree.
And that ordering is the whole point, right? That's what makes them useful for searching, insertion, deletion, hopefully fast.
Exactly. Usually O log n time
Mm.
on average, which is great. The sources cover the basic operations,
Yeah.
how you search, either recursively or iteratively,
How you insert new nodes, which always end up as leaves.
and deletion, which has those slightly fiddly cases depending on whether the node has 0, 1, or 2 children.
Yeah, deletion can be tricky.
It can. And the sources also mention traversals, like in-order traversal, which for a BST gives you the nodes in sorted order, a very neat property.
But there's a catch with BSTs, isn't there? They're not always O log n. The sources mention degeneracy.
Ah, yes. The potential downside, if you insert data in a specific order, like, say, already sorted data,
Right. Smallest, the next smallest,
right,
etc.
then the tree can become completely unbalanced. It essentially turns into just a linked list.
And then your search time goes from O log n to ON, which is bad.
Very bad. And that's why the sources mention balancing techniques, things like AVL trees, red-black trees, ways to automatically restructure the tree during insertions and deletions to guarantee it stays reasonably balanced and keeps that O log n performance.
Okay, so BSTs are about order, and balancing is about maintaining performance. Now, what about the other tree concept mentioned? This idea of a complete binary tree. That sounds like a different kind of property.
It is. It's about structural density, or saturation, as you put it. The definition in the source is quite specific. A complete binary tree is one where all levels are completely filled except possibly the last level. And crucially, on that last level, all the nodes must be as far to the left as possible. No gaps on the left.
Ah, okay, so you fill it top to bottom, left to right, without leaving any holes until you absolutely have to at the very end.
Exactly. It's like pouring water into a container. It fills up level by level from the left.
How does that compare to, say, a perfect binary tree or a full binary tree? The sources distinguish these.
Right. A perfect binary tree is stricter. Every level must be completely full. All leaves are at the same depth.
So a perfect triangle shape.
Pretty much. And a full binary tree is different again. That just means every node has either 0 children, it's a leaf, or exactly 2 children. No nodes with just 1 child.
Okay, so a tree could be full but not complete.
Yes. Imagine a full tree where the last level has nodes, but maybe there's a gap on the left side. It's full. All nodes have 0 or 2 children, but not complete because the last level isn't packed to the left. A perfect tree is always full and complete, though.
Got it. And the sources mention a really practical aspect of complete trees, their array representation.
Yes, this is a key advantage. Because they are so densely packed and left aligned, you can store a complete binary tree with n nodes perfectly in an array of size n. No wasted space.
And there are simple formulas to find children or parents.
Yep. If the root is at index 0 in the array, then the node at index I has its left child at 2i plus 1 and its right child at 2i plus 2. Going the other way, the parent of node I, if it's not the root, is at floor, I1, 2.
Super efficient. And that's why they're used for things like binary heaps, right?
Oh.
Which are used in heap sort.
Exactly. That array mapping is fundamental to how heaps work.
Okay, so you've got A000245 counting specific kinds of rooted trees. And we have these definitions for BSTs, ordered, maybe balanced, and complete trees, structurally dense, array-friendly. How do we really nail the connection? Is A000245 counting complete trees, or?
No, it's not directly counting all complete binary trees nor all BSTs. The connection is more subtle, but it comes back to those specific combinatorial interpretations from the OEIS. A000245 counts rooted trees that satisfy certain structural conditions, like the root having degree 2. And these conditions often arise naturally when you map other combinatorial objects, like those specific BIC paths, onto trees.
Can you maybe walk through that DIC path mapping? How does a path starting U relate to a tree structure?
Sure, let's try common mapping. You can build a rooted binary tree from a DIC path. Start at the root, read the path. Maybe a U step means go to the left child, create it if needed, and a D step means go to the right child of the parent of the current node, something like that. Staying above the axis ensures it's a valid tree.
Okay.
Now think about a DIC n+1 path that must start with U. In this mapping, the first U takes you from the root to its left child. The second U takes you from that node to its left child.
So forcing the path to start U forces the resulting tree to have a root with a left child, which itself has a left child. It imposes a structural constraint near the root.
Exactly, that's the link. A constraint on the combinatorial object, the path starting UU, translates directly into a structural constraint on the corresponding tree. Root has degree 1, his left child has degree 1, specifically a left child. The OEIS interpretations like root degree equals 2 or conditions on the rightmost path capture these kinds of structural features that arise from the underlying combinatorial definitions.
That makes sense. So a 00000245 counts trees with these specific features, which might arise from things like dick-path constraints, but it's not just counting all trees of a certain size or all complete trees.
Precisely. It's enumerating a specific structurally defined subclass of trees.
It really drives home how these sequences, even defined by formulas or relations, are fundamentally about counting structures. And the OEIS acts like a Rosetta Stone, translating the number sequence into pictures of these structures.
It really does. And exploring those connections listed on the OEIS page, like the links to intervals in the week order on SN or certain parking functions, just shows the breadth. A000245 connects to a whole ecosystem of complex combinatorial objects, many having graphical or tree-like representations.
Okay. Now, shifting gears slightly, one of the sources, I think the Reddit thread snippet, also touched on just calculating things within a tree, like summing node values. That's different from counting types of trees, right?
Yes, completely different, but also fundamental. That's
Yeah.
about working with a given tree data structure. Summing all node values is a common task.
How do you typically do that?
Well, you have to visit every node exactly once. So any standard tree traversal will work. You could do it recursively, pre-order, in-order, post-order, just adding the node's value as you visit it.
Or iteratively.
Or iteratively, maybe using a queue for a level order traversal like breadth first search,
Mm-hmm.
or even more advanced space-saving methods like Morris traversal. The point is, there are standard algorithms for processing data held within a tree structure.
Right. So the study of trees involves both their types and counts, like where A000245 fits in, and also how to operate on them, like summing nodes.
Exactly. Two sides of the same coin, structure and function.
Which brings us back to why this is all relevant for, say, a number theory student using the OEIS. Why should they care about dick paths and tree degrees?
Well, imagine you're a number theory student. You encounter a sequence, maybe from coefficients in a series,
Hmm.
or counting solutions to something. You look it up in the OEIS, maybe it's A000245.
Okay.
The OEIS doesn't just give you the next term. It gives you these connections. It tells you, hey, this sequence you found also counts these specific kinds of trees or these kinds of paths.
It provides context, a structural meaning behind the numbers.
Exactly. It shows that the abstract numbers are enumerating concrete objects that appear in combinatorics in computer science. Understanding that mapping how a path constraint leads to a tree constraint gives you a visual structural intuition for the sequence. It helps you see the patterns, not just calculate them.
So the OEIS acts as a bridge between number theory and discrete structures.
Precisely. It reveals the underlying unity. It shows how arithmetic, combinatorics, and structural mathematics are all deeply intertwined.
That's a great way to put it. So we've taken quite a journey here. Started with A000245, saw its link to Catalan numbers.
Unpacked its combinatorial interpretations from the OEIS, realizing it counts specific rooted tree structures.
Then we explored the language of binary trees, BSTs for order, complete trees for density.
Clarifying that A000245 counts specific subclasses, not just any tree, but trees defined by constraints often derived from related combinatorial objects like dick paths.
And we saw how the OEIS is really the key tool for uncovering these rich structural meanings hidden within number sequences.
It's indispensable for anyone wanting to see that bigger picture.
So here's a final thought to leave you with as you explore the OEIS further. What about other sequences you might find, even ones that seem purely arithmetic right now? Could they also be counting something structural? Maybe graphs, networks, geometric patterns, maybe even structures in biological data?
The connections are often there, waiting to be discovered. Keep digging.